All right, so to try to increase retention rates, the likelihood that a teacher stays a teacher from one year to the next. Okay, so that's the retention rate. Suppose that one of the school districts in Alaska wants to conduct an experiment to determine if giving teachers monthly bonuses of $200 will increase retention rates. The school district has 300 teachers. Describe a completely randomized design to compare the effectiveness of monthly bonuses on retention rates. Okay, so we have 300 teachers, and we want to see whether they have the bonus or not, right? So randomly assign them. Completely randomized design is that where you have your treatment groups, and then you have X amount of people, and you just want to break them up into groups randomly. Okay, you're not blocking for anything or anything like that. Okay, so here you're randomly assigning them to half of them to the monthly bonus, and the other half to will not receive the bonus, and then you just compare the retention groups. Okay, we're just describing the experiment. We're not like actually mapping it out or anything. Okay. Okay. All right. So randomly assign half of the 300 teachers to receive the monthly bonus The remaining teachers will not receive the bonus. At the end of the years, compare the retention rates of the groups. All right, there you go. So just description. So the researchers believe that the level of the school, elementary, middle, or high school may be a confounding variable in the study. Why might this be the case? All right, so depending on what type of teacher you are, they might affect whether or not that might affect whether or not you're going to continue teaching. Maybe there's one particular level of school that is challenging than another, perhaps, right? And so that might be something, a factor involved in why they're leaving the profession. Okay, so that might be a confounding variable. Okay, so the level of school may affect retention rate as different levels may have or may be more challenging than others, right? May vary on being challenging compared to others. Which would affect whether teachers leave the profession. All right, now it says describe an experiment that would account for the different levels of school. Okay, so that would so we're going to basically use those as blocks. Okay, so we're going to separate the teachers by the level. That way we can kind of account for the level and then randomly assign bonuses to half of the teachers in each level and do it that way. Okay. Okay. So we could do a randomized block design. In which the blocks are the level of school. Okay, so what we're going to do is separate teachers by level and randomly assign half of them. We're assign bonuses to half of the teachers in each block. The other half will not receive the bonus in each block. All right. At the end of year, oops. Okay. So at the end of the year, compare. We're going to compare retention rates within each block. And then across the 3 blocks. Okay, so there's your randomized block design. So part D, suppose there are 100 elementary school teachers, 100 middle school teachers, and 100 high school teachers in the district. Describe a process for randomly assigning the treatments to the subjects and each group. Okay, so we're going to describe the methods specifically. Okay, so we have 100 in each group. Okay, so we're going to assign teachers in each group. There's 100 in each group, so we're going to do, each of them are going to get a number from 1 to 100, okay? From in each group, a different number, a unique number. We're going to use a random number generator. To generate 50 different numbers between 1 and 100. Now the reason we do 50 is because in each group you're going to do 50 are going to be receive the bonus, 50 are not going to receive the bonus, okay? So assign teachers corresponding to numbers generated or selected to receive monthly bonus. Remaining teachers in that block receive no bonus. Repeat for each block. Okay, there you go. That's number 23. All right, so number 24, it says the athletic trainer for the high school soccer team is planning a study to investigate the comfortability of a new shin guard compared to the standard shin guard. There are 20 students on the soccer team willing to participate in the study. After wearing the shin guards for 3 full practice sessions, the players will rate the comfortability on a scale from 1 to 10. Identify the experimental units, the treatments, and the response variable. All right, so the EUs, we have 20 students on their soccer team, so 20 volunteers, right? So, okay, so EU 20 soccer player volunteers. All right, and then we have so treatments. Okay, so we got the new shin guard and standard shin guard. Okay, response variable, let's do it over here. All right, so the response variable is, well, how comfortable are they? Comfortability, right? So rating of comfortability, scale of 1 to 10. All right, so part B. The athletic trainer plans to have each player use both shin guards at the same time, one on the left shin and one on the right shin. What is the name of this experimental design? Okay, so here we have, we're using both and we're comparing them. So one on the left, one on the right. So that's a matched pairs. We're pairing them together to compare their effects, right? So each player, in this case, each subject has both treatments, right? Has the left and then the right. Or they have the standard shin guard and the new one, one on each shin. Okay, so this is a matched pairs. Design. Okay, each subject receives both treatments. So remember, match pairs is you can have each subject have both treatments, or you can have two similar subjects, and then having one treatment. Okay, so having one treatment and the other one has the other treatment. But you either pair them by similar subjects, or you take each subject individually, having both treatments. That's refers to as matched pairs design. So describe the process for randomly assigning the new shin guard and the standard shin guard to each player in the study. Okay. All right. So this one you can what you could do is when you have a particular player, you can use a coin to determine whether they're going to use the new shin guard on the left or the new shin guard on the right, or vice versa, right? So you can use that to determine what kind of treatment they're going to get, or well, they're going to get both treatments, but in which leg will they receive which treatment? Okay. Okay. So we're going to say for each player, toss a coin to determine which shin receives which guard or shin guard. If a coin lands on heads, we can just say, okay, well, maybe the new shin guard is on the left, okay? New shin guard will be on the left shin, and standard guard on the right shin. If tails, new shin guard will be on the right shin, and standard guard on the left. Okay, so this is just kind of randomizing that treatment. Repeat for all 20 players. All right, so what is one advantage of this experimental design over, for example, a completely randomized design? Okay, So here we're in the match pairs, we're comparing right to left shin, right? We're comparing them to see. So and also we're doing this for all players. Okay, so that's important. Is that all players are comparing the right shin to the left shin, and then the rating, the criteria, the rating for comfortability that they're doing will be the same from 1 to 10. So this will be able to we'll be able to compare more precisely. Okay, so um, we will be doing this for all players to compare left and right shins. Producing a more precise estimate of rating of comfortability. Otherwise, it is possible. So if we did a completely randomized design, it's possible that we could have players of a certain characteristic that get assigned the same type of shin guard. Maybe the players that are more sensitive all get assigned to the regular shin guard, and then that's going to impact the results. You know what I'm saying? So it is possible that same type of players, i.e., for example, more sensitive, get assigned to same shin guard. Okay, if that happens, then that's going to impact our results, right? So we want to keep that in mind. All right, so number 25, a physical therapist plans to conduct an experiment using a randomized block design with patients from her clinic to determine effectiveness of 2 different exercises on reducing joint pain and increasing mobility. She's considering 2 variables to create the blocks. We have age of the patients, under 50 years old and 50 or more, and a time appointment, morning and afternoon. Which variable should be chosen to create the blocks and why? So you got to see which variable, the age or the time of the appointment, is going to affect the mobility of the joints. Okay, so which one is gonna affect it more? Okay, well, probably the age. If they're young, then they're probably going to have more mobility of joints, and versus when they're old, they're probably going to affect the mobility, right? And so we want to be able to use that as the variable. That's going to be the better variable, okay? So age of patients is more likely to have an effect on joint pain and mobility. Okay, so what is one advantage of using a randomized block design compared to a completely randomized design? Okay, remember, randomized block design has less variability. Okay, which is what we want. Okay, so randomized block design has less variability. Less variability is a good thing within each block. Which makes it easier to tell which type of exercise is most effective to reduce joint pain and increase mobility. otherwise, so if it's a completely randomized design, so otherwise, it's possible that we can get, for example, all older patients. If we get all older patients when we randomize them, then that's gonna affect our results because they're gonna already have joint pain because of their age potentially, and that's gonna make it hard to tell if the exercise helped, right? It's possible that all subjects are older, and may already have joint pain. Or more joint pain, I guess we should say, right? Okay, already. Okay, sorry about that. It's just taking a while. May already have more joint pain, we should say. Okay, okay. More joint pain. So it would be harder so it'd be harder to tell if exercise was effective. Okay, but when you do a randomized block design, you can just compare the effects because you're breaking them by each block. So you're guaranteed to have old patients, you're guaranteed to have young patients, and everything in between, right? All right, so 26 option, so it says farmer wants to investigate, so you have a couple options here, option 1, option 2. A farmer wants to investigate the effectiveness of 2 types of irrigation for increasing the growth of his crops. He has 12 plots of land available for the study. Okay, so we have 12 plots of land here, broken up. Some plots border a stream that runs from the farmhouse to the southern edge of the property. He plans to use a randomized block design to randomly assign half of the plots to one irrigation type and the other half of the plots to the other irrigation type. 2 options for blocking are shown in the diagram. For each option, one block is identified by the gray shaded area region and the other block is by the white shaded region. Okay, so option 1, he's blocking it by the column, right? Here, you're blocking it by those in the front versus those in the back. Okay, that makes sense. Okay, those are the 2 different options. Which blocking plan, option 1 or option 2, will better determine the effectiveness, excuse me, of the 2 types of irrigation? Okay, so in this case, it would probably be better to do all of the different ones here in this column. So option 1 would probably be better because if you're only doing the front, what happens if there's a difference between the front part of the land versus the back part of the land, right? Or like this part of the land. Whereas this one, you represent every single part of the land. I mean, you have half of it, but you represent every single part, the front and the back. Okay, and so I think that would be better, is because you have because the distance here, like for example, the ones here differ in distance from the stream compared to the ones in the back, right? And so because of that, that may affect, the quality of the land. Okay, and so we want to control for that. Okay, so here we're going to say option 1 is better. Okay, so the distance from the stream may affect crop growth. So this option, which is option 1, right? This option guarantees that each type of plot, whether it's near the stream, whether it's far away from the stream, would receive the treatment. Would receive both types of irrigation. Reducing variability. And determining which treatment is more effective. Okay. All right. So here it says, look at the here. It says, some plots border a stream that runs from the farmhouse to the southern edge of the property, right? Okay. So if you look at the picture, if you have the stream, for example, yeah, stream going here, like it says in that picture where it's going like that, right? Then you have your plots of land. So you have your stream. Well, you have, if you to do option two, well, then, okay, so then option two, you have, okay, well, you have ones, these guys all receive the same type of treatment, the white and then the gray. But if you look at this option right here, you have ones that are, for example, closer to the stream versus ones farther away from the stream. Right? All of them are represented. So you have all of them that are the same, that are different distances, right? All of these here are represented. All of these here are represented, and then they both get this. They both get the different treatments. Okay, and what we want to do to make this more effective is we want to see. Okay, well, let's randomize it so that, for example, this what happens if we randomize it to do a coin toss to see if, like, okay, this one gets that irrigation, this one gets the other irrigation, so to make it more random, right? So let's go ahead and draw an outline for the experiment. So we have how many plots of land? We have 2, 4, 6, 8. We have 10, 12 plots of land. Okay, so we got 12 plots of land, and we're breaking them into two blocks, right? So block one, plots by the stream, and block two, plots not by the stream. Okay, and then we have here random assignment. Okay, so now we're going to split them up, right? So we have group one, we have, let's see here. We have 2, 4, 6 plots here, and then 6 plots here. So what we're going to do is we're going to break them up by group, right? So we have groups here, 2 groups, one's near the stream, one's far away from the stream, right? So those are going to be our blocks. And then we're going to pick, for example, we're going to do, since there's 6 on each side, 6 in each block, we're just going to do 3 that receive a treatment, 3 that receives the other treatment, okay? So we have 3 plots receiving a particular treatment, which a particular type of irrigation, and then the other one, we have another 3 plots. Well, okay. And then this group is another 3 plots. Again, it's the same deal. All right, and then what we're going to do is this one gets a particular type of irrigation. So irrigation type 1, irrigation type 2, and you're going to compare crop growth. Okay, same thing here. irrigation type 1, irrigation type 2, compare crop growth, and then compare across. All right, there you go. So there's an outline. Sorry about that if you're running low on space. So what's the purpose of randomly assigning within each block? Okay, so random assignment, it tends to balance the effects of confounding variables. For example, I don't know, sunlight, soil quality, etc. Right? All these variables, it helps balance those effects. So differences in crop growth can be linked to the treatment type for possible cause and effect. Okay, there you go. So that's the little experiment there. All right, so number 27, according to pregnancy tracking apps, there are a few predictors for determining a baby's biological sex before the anatomy scan at 20 weeks, but do they actually work? One example is the ring test, where the mother holds a dangling ring attached to a thread of string over the belly. If it swings in a circular motion, it's a girl. If it moves back and forth like a pendulum, it's a boy. Suppose we sampled 100 women who did the ring test prior to giving birth, and 56 of them predicted the sex correctly. A simulation was performed under the assumption that someone is just guessing. If they were just guessing, then that means it's 50-50 chance, right? So 50%. The graph shows the results of 200 trials of the simulation. Okay, so this is assuming 50%. How likely is it to guess that 56 of them, whatever, correct, predicted the sex correctly? This is 56 out of 100. So 56 out of 100 is 56%, right? So 56% did it correctly. All right, so what does the dot above 61% represent? So this is the 61 here. All right, so let's go ahead and interpret that. So that's one simulation, okay? So in one simulation or simulated sample, of each sample had how many women? It was 100 women, okay? That's according to that. So in a simulated sample of 100 women, 61 correctly guessed the baby's sex by guessing. Oh, I guess I should say, just so I don't use the same word again, correctly predicted, right? Predicted the baby sex by just guessing, okay? They just guessed. Okay. All right. All right, and then so that's for that one. And then let's look at part B. What percent of the 200 trials resulted in a percent correct of 56% or more? So that's what we were saying, is that 56% guessed that it was, they guessed it correctly. Not in part A, but here, right? Suppose we sampled 100 women and then 56 of them predicted the sex correctly. So we want to see how likely is it that if they were guessing that you would get that result, right? 56% or higher. Okay, so 56% or more. So what's the chances of getting 56% or more? Well, in this case, we're going to need to count the dots, right? So, okay, so there's like 24 dots there. Is it 24? Count it. Yeah, 24. And then there's 200 dots. So that means 24 out of 200 is equal to 12%. Okay, so 12% chance. Which you remember it's greater than the 5%. Remember that 5% that we said? Okay, so because it's greater than 5%, that means that it's not statistically significant. So what that means is that it could have occurred by chance. They could have just, there's a good chance that they were just guessing, and that's why they got that result. And so we can't really say that it's due to the treatment, whether it's the ring, where the ring test helps, because they would have predicted that correctly anyways, even without the ring treatment. Okay, there's a good chance that they would have been able to predict it. Okay, so it's just not convincing enough evidence, right? So do the results from our sample 100 women provide convincing evidence that the ring test is better at predicting than just guessing? So, okay, no convincing evidence. So, no. A sample of 56% or more correctly predict the baby's sex just by simply guessing. Could occur reasonably by chance. Again, because 12% is greater than 5%. Okay? So if it occurs by chance, then we can't say that it has convincing evidence. So what sample results would convince you that the ring test is an effective predictor of a baby sample? Okay, so what sample results would help you, would convince you? Okay, so the typical cutoff is any percent less than 5%. So for what we need is we would need fewer. So 10 out of 200 is 5%. So we would need less than that. So we would need fewer than 10 of the 200 trials in the simulation. To be 59% or greater. Okay. To provide convincing evidence of ring tests effectiveness. Okay. All right. So then if we instead sample the 500 women, and again, 56% correctly predicted the sex of the baby with the ring test, would we be more convinced or less convinced of the ring test's effectiveness? So actually, if we had more women and we still got 56%, that actually means that we would be more convinced because 56% is greater than 50%. If you were just guessing, it would be a 50% shot. However, if you have a lot of women that are sampled and then you get 56%, which is above 50%, that actually gives more evidence that it's more effective, okay? Because remember, as you increase the sample size, the variability should decrease. And so because the variability decreases, we get a more accurate, we get a better idea of the effectiveness of the treatment or not. And if we still get 56%, that means that there's probably something going on here, that the treatment may impact their guessing, okay, or may impact their prediction. So it would be more convincing As sample size increases, variability decreases. Making it less likely for the sample proportion to be 56% or greater by simply guessing. Okay, in other words, if I look at this dot plot, if I have more women here in the study per thing, so if I have, for example, here it says 500 women, if we sampled instead 500 women, right, as opposed to 100 women in each sample, what that's going to do is that's going to decrease the variability. So it's going to make the curve more tight. And as a result, we're going to have less dots here. And because we have less dots there, that means we're going to have more convincing evidence. Okay, hopefully that makes sense. Okay, all right, so let me just get rid of that. But if we have less sample size, then it's going to be more spread out. All right, number 28. A recent study was done to determine if consuming peanut products during infancy could reduce the likelihood of developing a peanut allergy. From age 6 months to 5 years, half of the 600 infants susceptible to allergies who participated in the study were randomly assigned to avoid peanuts, and the remaining at least 6 grams of peanut protein weekly were consumed. At 5 years of age, the researchers monitored the children while they consumed peanut products in a controlled environment. 17.3% who completely avoided had developed a peanut allergy, compared to 3.2% with regular peanut exposure. Which type of experiment is described in this scenario? Okay, well, we have random assignment to two treatment groups. So we definitely know it's an experiment. And what type of experiment? Well, they didn't block for anything. They just simply took 600 infants and randomly assigned them to two groups, to the treatment groups. So that's just a simple or a completely randomized design. Okay. So completely randomized design. Okay. The explanatory variable is the level of exposure to peanuts. Level of peanut exposure. And then response is development of peanut allergy. Okay. So calculate the difference in percent of children who developed a peanut allergy. The difference in percent. Okay. So in between the two groups. So they said 17% in one group versus 3.2% in the other group. So we're just simply subtracting them. 14.1%. And we want to see if that difference is statistically significant. Is that significant enough? You know, that's the idea. A statistical test is determined to determine the probability of observing the difference of 14.1% or larger. The probability of that is less than 0.01%, assuming that there's no difference in the development of allergies between the two groups. Does this provide convincing evidence that early and regular exposure to peanuts will reduce the likelihood of developing a peanut allergy? Yes. 0.01% is less than 0.01% is much less than 5%. Okay, so because it's less than 5%, yes. So yes, these results are too unlikely to have occurred by chance. By chance alone. So there's convincing evidence that regular peanut exposure causes a difference in percent in development of peanut allergy. All right, so there you go. So in other words, our results are statistically significant. Let me just put that here, so you can remember your vocab terms. Okay. All right, here we go. So 29, a recent study was done to determine the effectiveness of different types of exercise on cardiovascular health. 406 adults with high blood pressure were recruited for the study. They are randomly assigned to complete an aerobics exercise, resistant exercise, combination of both, or no exercise over a 1 year period. At the end of a year, researchers determined the CVD risk profile for the participants based on several common factors. All right, so I identify the treatments. So the treatments are on the 4 exercise programs. We have the aerobic group, we have the resistance group, we had both, and we had none. Okay, so the 4 treatments. What is the purpose of including a group who did not complete a exercise program? Okay, the reason why we have the one that didn't complete an exercise program is we want to use that to compare against the ones that did. Okay, so this is the control group. So the number 4 is the control group. Okay, so to serve as a baseline to compare. Okay, oops. Okay, so this group is a control group used as a baseline CVD risk profile to compare with other groups who completed exercise programs. Okay. All right. So the researchers determined there was a statistically significant difference. Okay, in the CVD risk profiles for subjects who completed the aerobic and the combination program compared to control. Explain what this means in the context. Okay, so statistical significance means that the results were so large, the observed differences were so extreme or too large that it couldn't have just been due to chance alone. It had to have been due to the treatment. Okay, that's what statistically significant means. Okay, so the observed differences in CVD risk profile between aerobic and control group and between combo and control group were too large to have been due to chance alone. Okay, that's what statistical significance means. All right, so the difference was not statistically significant for the resistance only group compared to the control group. Explain what this means. Okay, so this means that the observed difference in CVD risk profile between resistance and control groups was not large enough to rule out chance alone. as an explanation, to rule out chance alone. Okay, that's it. I'm just going to do to rule out chance alone. Okay, yes, let me just do this here. All right, oops, sorry about that. Trying to do the eraser, it's not letting me. Just to rule out chance alone. Okay, so at one time, Spotify had a total of 9,000 employees. The CEO wanted to send a survey to 300 of these employees to measure job satisfaction. Describe a method for selecting a simple random sample of 300 employees. Okay, so all right, so we have 9,000 employees, right? And the CEO wanted to send a survey to 300 of them. Okay. Okay, so 9,000, 300. Okay, so we want a simple random sample. Okay. All right, so then label each number, right? So label each employee with unique number. There's 9,000 employees, so from 1 to 9,000. Use a random number generator. To select 300. Now we want to do, 300 people. So 300 different numbers between 1 and 9,000. Send a survey to each employee. Corresponding to number selected. All right, there you go. So what is the purpose of selecting a random sample? It should be representative of the population. So the CEO can generalize conclusions to all employees. That's the whole point of using the random selection. Okay, so if you do a simple random sample, because it's representative of the population, you can generalize it to all employees. And that's called the scope of inference. So number 31, an education research organization wants to conduct a survey of teachers to estimate their average annual salary, identify the population to which the results can be generalized. Okay, again, this is another scope of inference question. So you have a random sample of 100 teachers in the United States. Okay, so it's random and you have teachers. Okay, so that means in the United States. So because you took a random sample that you included randomization, right? That means that you can generalize this to all teachers. Okay, so all teachers in the United States, you can generalize it. A random sample of 100 high school teachers in Michigan, well, then you can only do the high school, you can only generalize it to all high school teachers, specifically high school teachers, and specifically Michigan. So all high school teachers in Michigan. Because we didn't select from other states and things like that, we can only do for Michigan. Generalize the results. Now, a random sample of 100 high school teachers at an education conference, well, then that means that it's going to only be those teachers at the education conference, okay? So notice that our scope of inference is getting smaller and smaller as we're getting more specific. So all high school teachers at the education conference. Voluntary response sample. Oh, so it's no longer random. It's not random. So that makes an impact. So a volunteer response sample of 100 elementary school teachers in Michigan. So we cannot generalize this to a population. We can only apply the results to the teachers in the sample, the 100 teachers. Okay, so the results are only limited to those 100 teachers. We cannot generalize it. So can't generalize to any population beyond the 100 volunteers in the sample. Okay. E, it says a convenience sample. Again, that's non-random. Of 100 high school teachers at an education conference. You can't generalize, right? Because it's not random. So can't generalize to any population beyond 100 volunteers at the conference. Okay. All right, so we're wrapping this up here. So recent study revealed that teens who spend the most time on social media, 5 or more hours a day, are 40% more likely. It says 40% more likely to report symptoms of depression than teens who spend the least amount of time on social media, 1 hour or less per day. Is the study described an observational study or is it an experiment? Okay, well, they didn't. It's not like they told them to spend 5 hours on social media and then you spend 1 hour on social media. No, they didn't assign to. They didn't assign them to treatments. Okay, they didn't impose treatments. So this is an observational study. Because treatments were not imposed. On the teens. They were simply asked about social media use. And were not assigned to different levels of social media use. Can we conclude that more time spent on social media causes an increase in risk of depression? No, because it's not an experiment. Okay, so no, this is not an experiment with random assignment. So can't draw conclusions on cause and effect. Suppose 80 teens volunteered to participate in the experiment. Describe a process that would randomly assign the 80 teens to 2 treatment groups. Okay, so again, just a random assignment. So give each teen let me change this here. A unique number from 1 to 80. Use a random number generator to generate 40 two groups, so it's 40 each. 40 numbers. I always forget the different. So let me change that. 40. Okay. 40 different numbers between 1 and 80. Assign teens corresponding to numbers generated to use social media 5 hours a day. The rest of the 40 teens will be assigned to only 1 hour or less per day. Okay, so there's a random assignment. All right, and we got one last question for one of the responsibilities of astronauts on the ISS, the International Space Station, is to operate a robotic arm to perform tasks. Researchers wondered if administering a low dose of caffeine and exposing astronauts to blue-enriched white light would improve the robotic arm task performance. 16 volunteers were randomly assigned to several treatment groups: only caffeine, only white light, both caffeine and white light, or no caffeine or white light. The researchers found that the group with both caffeine and white light had the highest scores for task performance. Okay, so what conclusion can be made for the study? Well, they were randomly assigned. Okay, so because they were randomly assigned to the different groups, we could determine cause and effect. Okay, so we could say that it caused their performance to improve. Okay, so however, because they were volunteers, we can only apply it to those astronauts. Okay, so because we don't have random selection, or because we don't have individual randomization, that means that our results are limited to just those volunteers. But because we have random assignment, we can conclude cause and effect. Okay, so for only these 16 astronauts, so we can't generalize it to a population. We can only say for these 16 astronauts, because they were volunteers. For only these 16 astronauts, getting a low dose of caffeine and exposure to white light, or it was blue enriched white light, right? So let me change that to blue enriched white light caused their robotic arm task improvement, or performance to improve. All right, that's going to do it for the video, guys. Hope you found this useful and informative, and as usual, I'll see you in the next one.